One of the centerpieces of statistical mechanics is the so-called Maxwell-Boltzmann distribution. The Maxwell-Boltzmann distribution tells us that if a system has a certain temperature T, okay, and it is open to the environment in the sense that it can exchange energy with the environment. So energy is not a fixed value because it can exchange energy with the environment, but it is also made in thermal contact with the environment. Therefore, its temperature is fixed. It is equal to that of the environment. Given that condition, you can derive the so-called Maxwell-Boltzmann distribution, such that the probability of finding the system to assume a certain energy E is proportional to this exponential factor, e to the power negative E over kt. This is called the Boltzmann factor. Boltzmann factor. Like I said, this is one of the centerpieces of statistical mechanics. Its importance is impossible to overestimate. What that means is that if all else being the same, then the lower the energy of the system, the more likely you're going to find a system at that state. Okay, it doesn't mean the energy the system always assumes only the lowest possible energy, because there is a probability, even though a lower one, for the system to assume a higher amount of energy. This applies to many different types of systems, not only the ideal gas that we've been studying so far. We're going to look at two drastically different examples of Maxwell-Boltzmann distribution. The first example has nothing to do with ideal gas, okay? Because in ideal gas, the energy E for each molecule is 1/2 mv squared, right? And V is a continuous variable, therefore E is also a continuous variable. There are infinite possible number of energy values. Here, we have what's called a two-level system, okay? Which is very common in modern physics. Two-level system. Say what's going on inside an atom, okay? This system has only two possible values of energies, E1 and E2. The energy gap between them is delta E. Suppose I have n particles, okay? Each of these particles can either live in the lower energy level or at the upper energy level. There's an energy gap of delta E. And my question is, if the system satisfies the Boltzmann distribution, how many of these particles will be found in the lower energy state, and how many of them will be found in the upper energy state? Now, it is clear, based on the Maxwell-Boltzmann distribution, that more particles will be found in the lower energy state, less will be found in the upper energy state. That's for sure. But the question is, what is the ratio? Okay, is it 60-40, or is it 90 and 10%, and so on? Let's take a look. Okay, let's say the probability of finding this particle in the lower energy state is P1. Now we know that P1 is proportional to e to the negative E1 over kt. Right? K is the Boltzmann factor. Proportional to. What about P2? Well, P2 is the probability of finding a molecule or a particle to be in the upper energy state. That's P2. P2 is proportional to e to the negative E2 over kt. Right? Now, I am supposed to use proportionality symbol, not equal symbol. Why? Because it's only proportional to. The difference between proportionality and equality is that you have a constant missing, okay? A constant missing. So I should write P1 equals constant times this, and P2 equals a constant times that. Now that constant is not necessarily equal to 1. How does one determine that constant? Actually, the idea is very simple. You want to determine that constant such that the total probability of finding a molecule, a particle, either in the upper or in a lower state is equal to what? Well, that would be 100%, right? Because, you know, there are only two possible states. If you're not here, it must be there, and so forth. So P1 plus P2 must be equal to 100%, okay? Because there is not a third state available for that system. So I have P1 plus P2 equals 1, okay? That is a required condition, and that is called a normalization condition. And constant C is also called the normalization constant. So I can find that normalization constant C based on this condition. So P1 plus P2 equals C e to the negative E1 over KT plus C e to the negative E2 over KT. And that equals 1, right? By normalization condition. I can solve for C instantly. Okay, what's C equal to? C equals to 1 over e to the negative E1 over KT plus e to the negative E2 over KT. Okay, I can then plug that C back into the expression for P1 and P2. I can get a complete solution for P1 and P2. So for example, P1, what is that equal to? That's C times e to the negative E1 over KT, right? So it's e to the negative E1 over KT divided by e to the negative E1 over KT plus e to the negative E2 over KT. Okay, I can simplify this a little further here. You notice that you got E1, E1, and E2. What if I multiply every term in the numerator denominator by the same factor? That's e to the positive E1 over KT. So this is 1, right? This is 1, and this is also 1. What's next? E to the negative. Okay, negative E2 over KT times positive E1 over KT. Isn't that delta E over KT? Here again, delta E equals E2 minus E1. Same thing. Okay, now delta E is a positive value, and therefore this e to the whatever that thing, okay, that's greater. That's a positive value. So 1 plus something. So this is less than 1. That makes sense because P1 itself cannot be equal or greater than 1 because there is also P2. Okay, the probability of finding a particle upstairs. You can also see how P1 changes as delta E and T changes. What's important is the ratio of delta E over KT. Okay, now suppose one fixed delta E. Okay, suppose one fixed delta E. So delta E is fixed. As T rises, okay, the temperature becomes very high. What happens? Well, then delta E over KT is almost equal to 0, right? E to the power 0, what's that? E to the power 0, that's 1. Then P1 approaches what? 1 over 1 plus 1. It's 1/2. What does that tell you? It tells you that at very, very high temperature, very high temperature, half of the molecules will be downstairs and half the molecules will be upstairs. So you got equal distribution upstairs and downstairs. Of course, that is when the temperature is very high. When the temperature is really low, you can imagine most of the molecule will be downstairs, and that indeed is true. When temperature is really low, take a look at this. Okay, delta E is positive, T is also positive, but delta E is far greater than KT now because T is very small. You have e to the power negative infinity almost. What's e to the power negative infinity? That is almost equal to 0, right? So P1 is almost equal to 1. What does that tell you? Nearly 100% of the particles are downstairs and almost nothing is upstairs. So let's take a look at this general trend. You start with 2 levels, okay, E1 and E2. At very low temperature, almost all particles are downstairs. Nothing is upstairs, pretty much. And then as you raise the temperature, you'll find some particle will make a jump to upstairs. And more particles go upstairs until when temperature is positive infinity, you'll find that 50% of the particles will make its way up, the other 50% is still down there. Okay, so you see, E1, as long as E1 is less than E2, the number of particles downstairs is always greater than the number of particles upstairs. But as temperature rises, more particles will be excited from the lower energy state into the upper energy state. This is what the Boltzmann distribution tells us. All right, here's something very interesting. even at absolute infinite temperature, positive temperature, you find that number of particles upstairs still does not exceed the number of particles downstairs. It's going to be 50-50, right? As a matter of fact, you can find n2 over n1, n2 the number of particles up here, n2 the number of particles down there, is equal to e to the negative delta E over kt. As long as delta E is positive, which we know, delta E is the energy gap, right? And T is positive. You have a positive ratio here with a negative sign that is always less than 1, okay? As long as T is positive. Is it possible we can pump more particles upstairs, leaving less particles downstairs, so that you have achieved what's called population inversion? You totally reverse the order. N2 is greater than N1. Well, mathematically, if you insist on using this formula, you find that this is only mathematically possible if T is less than 0, right? You have, if T is less than 0, delta E is always positive, right? You get an overall positive thing, and then of course you can be greater than 0. But the question is, that will mean we have what's called a negative temperature. Is there such a thing as negative temperature? Well, this is an interesting topic that we'll cover a little bit more later.